Morning, everybody. So in the previous section, we have discussed how to determine the expected shortfall, and under the normality assumption, we end up to have, let's say, the var is mu plus sigma, the z value. The expected value, on the other hand, will be at the level of alpha, so we end up to have a phi z over the alpha. So this is basically the average value, okay? The average value of the negative infinity until the alpha or the var position, right? A var position. This is the expected value. So now we're going to discuss about under the student T assumption. Okay, what is the expected shortfall? The level alpha. Okay, so that is what we want to do. So in this session, we're talking about the expected shortfall under the student T assumption. Okay, so this is the core contents of this particular session. So first of all, we just have a quick review on the difference between the expected shortfall and the value at risk. Okay, so basically, you're going to have a return series, okay, with such, let's say, distribution. So you have a return here, then you have the PDF, probability density function involved. So the expected shortfall most probably will refer to, let's say this is the 5% var, right? var at the level alpha. And then most probably the expected shortfall you're going to find out is a smaller value with E of S alpha, because this value, expected shortfall will always fall within the minus infinity to VAR alpha. Okay, so this will be the value involved. Okay, so the expected shortfall should be always smaller than the value at risk, right? So R here representing the, so this define R. R is the portfolio returns. Right? You're talking about a group of investment assets. So this is the overall returns, okay? Where this distribution will follow student T distribution. Okay. So similar to the previous assumption, we have, or let's say the Z normalization is T value. Of course, this will be the T value. Okay. So the process is the same, but now we are referring to the T value, okay, with the degree of freedom mu. So for the normality, normal assumption, so we have mu plus Z alpha sigma Z. So for student T, so this will be mu plus the T value. So once you want to determine the expected shortfall, okay, then you will end up to have ES of alpha. Okay? So you're going to have a mu plus sigma. So since this is the expected value, expected shortfall, you're going to have the T value actually. So let's say we still use the Z now, right? for the variables. So this is z less than the t value, t mu of alpha. So this is not the z value, this is actually the t value. Right? Z just a variable, right? This is a variable. So what is the e of z? So this value basically is, or let's say we have this q value. This q value basically referring to the quanta involved. So you're going to integrate from minus infinity to the t value. So using the expected value definition, you have a z f t of mu z dz. So this actually can be written as t, right? Because z normally we're referring to the standard normal z value, but this one is actually the t value involved. Right? So this is actually t subject to or given by zt. Also, this should be a t value actually. So let's say we just still use z value. Therefore, you can compare the z or the e of s with the z value we have defined earlier. Right? This one. Right? So this one we're using the z value. Of course, this one is student t, but still we use the random variable z, which is actually the t. Okay. Okay. Now we're going to find out this particular value. Okay, this integral. So the student t is going to have a, let's say we use the student t PDF. So you're going to use exactly the same methods. So for z value, we use the PDF for standard normal distribution. Okay, standard normal variable. Okay, this is the one. So now, if you use the student t, then you must use the PDF of student t. The f of mu with alpha. Or you can say this is mu. Right? So for the z value, instead of using t, we use z here. Right? So you have tau of mu plus 1 over 2 over mu pi. So then you have 1 plus z square over the mu power of mu plus 1 over 2. Okay, so this is the of course, the first whole term here is actually a constant without z, the z. Then we can use the CV here, right, to simplify the equation. Not really simplify. Okay, based on this, we're going to do some substitution to simplify the integration afterwards. So let's say we have substitute the u. Substitution. So let's say I have the u equate to 1 plus z squared over the mu. So this one, if I differentiate this with respect to du dv, du dz, then this will be 2z over the mu over the dz. So now we want the z dz can be written as z dz is actually mu over 2 d. Okay, so this is the result we want. Okay. So then we can just find out the expected value I. We just use the I for the expected value. So this is the expected value. But this expected value, of course, is not the overall of this. This is just this particular part. Okay, this particular part without the alpha. Right? So I will be CV. Then you integrate from u minus infinity. So the value is from minus infinity to var alpha, is it? Okay. Or the probability q here. Okay? Q. So basically you have the q. So from minus infinity to q. Or this is a quanta of var, okay, q. So you have a mu over 2. Then you have u power minus mu plus 1 over 2 d. Is it? So obviously when u go to infinity, so your u basically will be, if z go to infinity, then u will be positive infinity, right? Because you have square here, so you have always a positive infinity. When the z is q, then this equation will go back to 1 plus q square over mu. Right? This will be the value. Then we substitute this back to the equation here. Then you're going to have minus CV. So now we just put minus infinity to positive infinity. So we just change the limit from here to here, then from q to minus infinity. So we can just exchange the value from minus infinity. So this is uq. So this is mu over 2. Okay. So now we can find out the integration of this part. Okay. So for the minor part of this, if you want to integrate integration uq to, or just u minus the mu plus 1 over 2, so you just do the inner part of this, this part. Since the mu is a constant, integrate this. So integrate this, you actually have differentiate this, you're going to have minus mu over 2, isn't it? Plus 1. Okay? Integrate this, you have minus mu plus 1 over 2 plus 1. Okay? So you have plus 1, basically the negative and positive. So in this case, you end up to have mu minus. So now you have mu minus 1 over 2. Okay? After plus 1, okay? After plus 1, the negative becomes the value. Okay? This is plus 1, which is a minus 1. Okay? Minus 1. Then this whole thing divided by 2. So this is after differentiation of this. You get mu minus 1, 2. Okay. So overall, you can just write minus, this one is bring it up. Then you have mu minus 1. Okay. So this is the integration of this part. Right? Now we substitute the limits inside this in order to get the I value. Isn't it? Maybe this use I. So the expected value now minus CV mu over 2, which is a constant. Then again 2 over the mu minus 1. So this is from uq to positive infinity. Okay? So if you substitute infinity to u, then this is 1 over u. So this will become 0. Okay? So then you have 0 minus uq to this value u. Then the minus minus become positive. this will become minus CV. So it's 2 over u minus 1, the same value. So this one is u now become 1 plus u square over mu, then the whole thing power of minus u minus 1. So this is the u value, this is the u value. Substitute back to it. So minus minus, this inner part will become positive. This is 0 minus minus, so it becomes positive. So in the end, take out the value mu minus 1. So 2 will be cancelled. So we can simplify the result in the form of. So this is our expected value for this particular part. Okay, this part. So you just divide by 1 over alpha afterwards. Okay. Okay. So later, we know that our ft just now for z or q, let's say. Okay. So this is CV 1 plus q square over the b. So this is plus 1. This one is minus 1. This is plus 1. So when you redo this, 1 plus q square over the mu minus mu minus 1 over 2, which is this term. So what you need to do is just multiply 1 plus q square power plus 1. Okay, power 1, then you have 1 plus q square multiply. This is still minus 1 before you simplify everything. Okay. So you just substitute this I here. This is your I, then supposed to be minus mu minus power mu minus 1. Now if you do this, this will be plus 1 and the whole thing, isn't it? So the mu minus 1 becomes mu plus 1 after that. Okay, so this basically will be, sorry, this will be plus 1. This will be plus 1. Because this one is minus 1. If you have plus 1, then this equivalent to this. This is the mu, the degree of freedom. Okay, now we can just substitute back or change this back to the ft. Okay? So this CV times this one is actually your, so you have the ft, and in your integration you can write I is mu over mu minus 1, which is this value here. This is 1 plus q square over mu. So the CV times this term is the ft. Okay, so now we go back to the ft here. Okay, now we have I in terms of the PDF and a constant in front of it. Okay, so in your expected value, ex, es. So we just go back to the expected value first. Then you have z less than q, which is the expected value over the average value alpha. Then you have this whole term here. Okay? Then you have ft or actually we can just okay, so this is a bit fast. Maybe you can just go back one step. Then we should be able to get, this is your I. So your I basically is this. So we have multiplied mu here. So this mu plus QC over the mu. So mu cancel the mu. You end up to have 1 over. So you have mu minus 1. Then this will be, this is negative. This is negative. So you have mu plus Q squared. Okay, this one is mu plus Q squared. Okay, and then the FT, the PDF. So now you have the expected value. We can substitute this back to the E of S, expectation for alpha with mu plus sigma the E of Z less than Q. Okay, this is the value. But here we just refer back to the T value instead of the Q, which is the same value actually. Okay? But this one we're talking about the alpha. So the degree of freedom first, then the alpha. So we just refer back to alpha here. So then we just substitute the value. So E of Z is basically this value, right? Sigma, then you have mu minus 1 times alpha. So this is mu plus Q, actually is the T value, power 2. The T value power 2, then the PDF. So this is not Q but T value. So this Q actually is the T value, T at the probability or critical value alpha. So at the end, if you want to rewrite everything back, so the FT is actually the CV, or the original equation is this basically. So we just expand everything again. This is the mu. Expand everything again. We bring this back to the equation below here. Then finally we were able to get mu plus sigma. So this is mu plus T over the mu minus 1 alpha. Then the mu plus 1 over 2. So this is a PDF value. It's a PDF value. Then you have the mu of pi gamma mu over 2. So this is the PDF form. Then this is minus mu plus 1 over. Okay, so this is the overall expected shortfall under the student T assumption. Okay guys, so it's slightly different from the normal assumption, which is I think in terms of equation you can just expand this to the PDF for standard normal distribution. Okay, so this is basically the Z value after that. So you just need the T value to solve the problem. So this Q actually can go back to alpha square instead of Q. This you can use alpha square. Okay guys, so this will be two assumptions under normality and student T distribution derivation of the expected shortfall at the level of alpha. Okay, level alpha. Okay, in the following session, we're going to have some numerical examples to calculate the expected shortfall under the student T and normal DT assumption. Okay, till then, bye bye. See you guys in the next session. Bye.